to YouTube. So thank you. I pass it on to Hannah to introduce the last speaker of the day. Hannah, please.
Yep. All right. So we continue with the last speaker, and the last speaker of today is Andrea Giladi. And Andrea is a research fellow in statistics at the University of Milano, and his research interests include spatial and spatio-temporal models on road networks, focusing on aerial and point process models. And he is the co-author of 2 R packages, which are OSM extract and SF networks. And SF networks is also the topic of Andrea's presentation today. And I hand over to you, Andrea.
Okay, thank you very much for the introduction. One moment that I share the screen. Here. Is it working?
Yeah, it works.
Okay, perfect. Here is not working, but I can do anything like that. Okay, so again, thank you very much for the introduction. I'm here to present the talk, which is entitled SF Networks, Tidy Geospatial Networks in R. And in this talk, I will present the R package SF Networks. The R package SF network focuses on the analysis and the data management of geospatial networks in R using a tidy workflow. This is a package that was developed by me and several amazing colleagues, which are named Luke, Lorena, and Robin. So first, I want to share some link. The first link is for the, let's say, the online version of these slides. Just give me a moment. Should be working. And the second link is for the GitHub repository, where there is these slides, the code behind the slides, the code behind a demo, and that I will run during the presentation, and also the data that will be used for the presentation. Again, just give me 1 minute. Okay. Oops. Then let's say this is the schedule for the talk, hopefully. At the beginning, I want to introduce the package, then I want to introduce what are geospatial networks, and I want to introduce the motivation and the ideas that led to the development of this package. Then we will switch to our studio and we will try to code the first few examples using the package. Then we will go back to the slides. In the second part of the slides, I will present some, let's say, pre-processing steps that we developed ad hoc for the geospatial networks. And I think these ad hoc function, these pre-processing steps are really important when you work with geospatial data, especially if the data is obtained from OpenStreetMap. At the end, we will go back to the R code and we will answer some question if there is any question, or we will try to code the solution to the challenge for this conference if there is time. I just want to point out that this talk and the corresponding, let's say, interactive R coding session is based on the developed version of the package. You can install the developed version of the package from GitHub. You just need to run this line of code. Okay, so we can start now. The package SF Networks is based on the analysis and the management of geospatial networks in R using a tidy workflow. And so first I want to start talking about geospatial networks. Geospatial networks are graphs that are embedded in a geographical space. So first they are graphs, meaning that they have nodes and edges, and they are also embedded in a geographical space, meaning that their nodes and edges are associated or are located in some space. For example, here in this figure, I represented this 3D river network of all over the world. And I think that you can easily imagine that this river network can represent it as a geospatial network where the intersection among the rivers is represented node for the graph network, for the graph part. and the river themselves represent the edges for this network, for this geospatial network. Here it's important since the nodes for this network are usually represented as points. The edges for this type of network, at least in our representation, are represented as line string. There is no, let's say, strict restriction that the nodes must be points and the edges must be line string, but as far as I know, this is the most common approach, and for the moment, this is the only approach supported in our package. Lastly, I want to stress that this type of data is quite common. For example, I usually work with street networks, which are probably the most common example of geospatial networks. And nevertheless, I mean, there are several examples of geospatial networks in ecology or in transport, for example. This distinction is quite important since usually when you analyze graph data, you may be interested in the topology of the network. This is not always true since, for example, for this type of network, for geospatial network, you are interested both in the topological structure and the spatial structure, since the topological description of the data is not enough to completely describe this type of networks. So the package, as I said, implements a tidy workflow, and I mean here I just want to super briefly introduce and what is the tidy workflow. I mean, I'm pretty sure that you all know what I'm talking about. I just want to super briefly present the tidyverse. The tidyverse is a collection of packages for data science. All packages in the tidyverse share a common philosophy, and I think that the core structure behind the tidyverse is the idea of the tidy data structure. The idea of the tidy data structure is that we have that for the, let's say, the classical tabular data, each row of the tabular data represents one observation. Each column of this tabular data represents one variable. On the left, we represent, let's say, a super simple example showing both, let's say, the data frame equivalent for the tidyverse, which are the tables, and we also present one of the common deep layer curves, which is called select. So we have this chain of operation where we start from an object. Roxel is an SF object, which is stored in the SF networks package. And this chain operation is just used to present that the Roxel is stored as a tidy object, where each observation represents a street segment. Each column represents a characteristic of the street segment. In this case, the name of the road and the classification of the street segment. Also, in this case, we have that Roxel. I mean, I forgot to say that, but Roxel is, let's say, a subset of a road network somewhere in Germany, I'm not sure. And Roxel is an SF object. So, as I said, this SF network packages focuses on geospatial network. So there is a spatial component and there is a graph component. For the spatial component, we adopted the SF package. The SF package, I mean, you all know what I'm talking about, and the SF package is an R package for spatial data science. In the SF package, there is a standardization of the geographical features, for example, points, lines, and polygons, which are represented using the so-called simple features. The package also implements geometric and spatial operation like intersections, union, differences, or jittering of points, for example. In the left, we show the printing of an SF object, which again is Roxel. We can see that for this type of object is a line string object. We can see that, I mean, the particular bounding box, we can see the coordinate reference system of the object. And we can see that in this case, for the Roxel data, there is a series of segments. For each segment, we have a classification, and also for each segment, we have like its displacement on the Earth or its location. In this case, again, we have like a tidy representation of the spatial data where each segment has its own row and each characteristic of this segment has its own columns. This is quite important since in the SF package, the dplyr and the tidyr verbs are usually implemented, and usually it's pretty easy to just work, usually they just work on SF objects. The second part of the geospatial networks are the networks. For the networks, we use the tidygraph package. The tidygraph package is a wrapper or a tidy interface to the iGraph package. The iGraph package, again, is a wrapper around the iGraph library, which I think is a C library. And it's probably the most, iGraph is probably the most important R package for graph analysis. In the tidygraph package, there is, the tidygraph package implements the idea that when you want to analyze a graph object, you model this graph object as a collection of two tibble or two tidy data frame objects. For example, we have here on the left, we create a tibble named nodes, which is just composed by 3 objects or 3 nodes. Then we create a tibble named edges, and these tibble named edges describe the connection among the nodes. And then we create a tibble graph object. A tibble graph object is the union of 2 tibbles. One tibble describes the node and one tibble describes the edges. In the edges table, there are always 2 columns which are named from and to. This column from and to says that the first edge connects the first node and the second node, and so on for all the other edges. And here, I just want to say that here it says that there is this node which is active, and I will add more details later. And that's all for here. So the SF network package implements, let's say, the union of these 2 approaches, creating a spatial, let's say, a spatial extension for the tidygraph package. The idea, the problem is that actually, even if the author of tidygraph implemented this interface, you cannot simply, let's say, extend the spatial component just adding a geometry column to the node or the edges. Since if you simply add the geometry column, the tidygraph function doesn't know how to work with this geometry column. So the idea of this package is to merge these 2 packages and create an extension that can work with the geospatial networks. So when the authors try to describe a tidy graph, they says that when you want to represent relational data, it's quite difficult to create a single tidy data object. So when you want to create a close approximation of tidiness for relational data, is 2 tidy data frames, one for the node and one for the edges. Then when we try to readapt this concept to geospatial network, we readapted this concept saying that a close approximation of tidiness for relational geospatial data are 2 SF objects, one for the node and one for the edges. So the SF network, the most important structure in the SF network package is the SF network class. The SF network class, there are several ways to create the SF network class. Here I will just present the simplest one. And in this case, we try to create an SF network object starting from the roxel data. Again, the roxel data are the line strings representing the road segment in a particular region in Munster. We can see that when we plot this type of data, we have both the spatial component. For example, here we have the CRS of the data or the geometry of the node and the edges, and the graph component. The graph component, since we have both a set of nodes and a set of edges. In this case, the SF network object is created by placing a node at the boundary point of each line string, and the edges are just a collection of all the line strings. So here in this case, we have a short description, and we have this representation for the roxel data. Okay, now I will just switch to the coding session. For the coding session, I just want to say that I will focus, the example that I will present are based on road networks, since I usually work with road networks and I work more or less every day with road networks. Nevertheless, the packages should work with every type of geospatial network. So there is no particular focus on road network, and it's not optimized for road networks. There are several examples of application of our package in other contexts, and I add here some example if you want some inspiration. So let's see if I can switch. Let's try one more time. Oops. Unfortunately, it seems that Git doesn't work at the moment, but I will update the slide as soon as possible. Just give me a moment that I have to increase the font. Oops. Fine. Okay, can you see now? I mean, I hope so. If you need a bigger font, just send me a message in the chat, please.
Looks good. Everything looks good.
Okay. So for the demo session, I mean, as I said, you can, the demo session is based on the development version of the package. The development version of the package can be installed from GitHub. So I don't have to install the package now. I just need to load some packages and set some options. The SF network package, as I said, is based on the union of SF and tidy graph. The SF package is used for the spatial analysis. The tidy graph is used for the graph analysis. SF network extends both the SF and the tidy graph function. So usually when you want to work with SF networks function, it's best to just load also the SF and tidy graph packages. I mean, ggplot is just for the plotting. Here, I mean, I load the Isle of Wight data. The Isle of Wight, the IOW object represents a subset of the street segments that are located in the road network of the Isle of Wight. I mean, in the majority of the road network of the Isle of Wight, according to a driving mode of transport, which means that I excluded the street segment that cannot be traveled using a driving mode of transport. The Isle of Wight is a small island located in the south of England. And I mean, it's probably my favorite example when I want to present a new concept or just test new ideas. So if we print the Isle of Wight object, we can see that it's a simple feature object. It's a simple feature collection with almost 4,000 features. This feature represents the segments of the network. Then we have, again, the bounding box and the coordinate reference system. Here, I just want to stress that in the SF network package, it should be, let's say, a general tool for geographical networks. So the analysis should work with any type of coordinate reference system. Nevertheless, if you want to move from SF network to other packages, for example, at the end, I will present something with SpatStat. If you want to move from SF networks to SpatStat, you must be sure that you are dealing with projected coordinates. So for example, in this case, we cannot simply translate this data to a road network in SpatStat. We need some preprocessing step, but I will add more details later. And then just plot the object. Oops, sorry. Okay, when we plot the object, we see, let's say, the skeleton of the island. We see more or less, I think it's pretty clear that there is, this is the skeleton of the road network structure. We see also that there are smaller, let's say, isolated segments here and there. These segments are not truly isolated. The problem is that these segments are connected to the other segments using other type of roads, which are not, let's say, part of this data set, or maybe they are just misclassified. So when we want to convert a line string object or an SF object with line string geometry with SF network object, we just have to use SF network. So I run this code. When we print the SF network object, we get a short summary of the SF network object. So we can see that in this case, this SF network object has 4,500 nodes and almost 4,000 edges. We have a summary of the coordinate reference system that is used to represent the data. And then we have a short description of the graph. In this case, it says that there is an interactive multi-graph with 900 components. And then we have a short description of the node table and the edges table. Here, when we created this type of data, we're starting from line string object, we have that the Isle of Wight object is just a simple feature object composed of several segments. When these segments are translated into a geospatial network object, then there is an algorithm behind this function that places a node at each unique boundary point of these segments, and the edges are just the input lines that were passed to the function. Since, for example, here, if you check this Isle of Wight object, the Isle of Wight object has 3,913 features, and the SFN object has 3,913 edges. When we check this data, we see that there is an active component. This active component is what is used by the tidy graph function for all the analysis, and we will have more details later on. As I said, for the SF network object is a union of SF and tidy graph object. So the tidy graph object describes the graph component of the data using two columns, the from and the to column. And for example, this means that these edges connected the first and this edge connected the first and the second node. The second edge connects the third and the first node, and the fourth node, and so on. There are a few more things. So here, when I created this object, I set directed equal to false. Directed equal to false creates a non-directed network. Here, you can see also from the printing of the object. If you want to create a directed network, just set directed equal to true, which is the default. I decided to set directed equal to false, since at the moment I think that it's not possible to mix directed and undirected edges. For example, it's not possible to mix one-way and two-way roads. So for the moment, for simplicity, I assume that each road is two-way. If you're working with road networks, it might be useful to mix one-way and two-way roads. And there is an example in the vignettes of the package that show how to deal with this situation. Lastly, we recently implemented two options that can be used to adjust the printing method. I mean, it's nothing major, but I think that it might be nice when you want to test and work with this type of object. So there are these two options which are used to tweak the number of features which are displayed for the active and inactive geometry. Here we can see that the node data are the active table, and there are two features displayed for the active table and just one feature for the inactive table. I will explain what means active or inactive in a few minutes. So now let's see a plot. Oops. Okay, the default method for plotting SF network object plots both the edges and the nodes. As you can see here, the nodes are located at the boundary points of the edges. The nodes are represented as black dots, and the edges are represented as lines. I think that this is also an even better representation to represent that this type of data, so the SF and the Isle of Wight data, can be represented as a geospatial network object. The plotting method is more or less just a wrap around the function, which is called plot.c. So the simple feature column geometry method for the plot function, and which means that we can tweak, let's say, a few parameters to adjust the plotting. For example, here I decrease, let's say, the size of the plots. I change the line type, and I change the type of the symbol of the symbols that are used to represent the nodes. Lorena also coded the method for the autoplot function, which means that you can also use ggplot and adjust a few things to plot SF network object. So for example, this is the plotted method from this line of code, and we can see that here we have changed the line type. And again, we have also an autoplot method. at the moment it's not possible, let's say, to adjust all the features for this type of plots, but there are other ways to create this type of plots, and I will explain these other ways at the beginning, or at the middle of this presentation, let's say. So now for the active and inactive geometries. As I said, for the tidy graph objects, when you represent the tidy graph object, there are two ways. There are two tables, one for the nodes and one for the edges. The problem is that when you want to work with this type of data, you always have to specify if you want to work, if you want to apply a function or a modification, or is called the morpher, to the nodes or to the edges. For this reason, the authors of Tidy Graph decided to, let's say, create this idea that when you work with the Tidy Graph object, there is always a table which is named active. The table which is named active is, let's say, the subject of the manipulation that are performed using this type of data. For example, let's say that you want to filter on, you want to add a column which describes something. If the nodes table is active, then this new column will be added to the node table. If the edges table is active, then this new column will be added to the edges table. This is particularly important since, I mean, some features, let's say, characteristics do make sense only if you're working with nodes or the edges. So you always must be sure that you are working with the active geometry, with the active table. By default, the node table is the active table, but we can use the function activate to switch which table is active. You can also use, let's say, this pipe function to perform a pipe operation where you set the nodes or the edges as the active table. For example, this line of code, when we print this line of code, we see that there is the same printing method, there is the same print as before, but in this case, the edge data represent the active data, so the active column. We can have, let's say, an equivalent operation if we say SFN, then pipe with the A, and then print. This operation again is the same and says that we want to print the SFN data, setting the edges table as the active table. The active table is always printed first in the printing of an SF network object. So now I plan to go back to the slides. Oops, sorry. So for this part of the slides, I hope that the basic idea behind SF networks is clear, and I hope that the basic concept and the basic class, which again is named SF network, is clear. For this part of this presentation, I want to present a set of functions or a set of morphers which are used to manipulate the network. I think that these morphers are quite important, since usually when you want to work with this type of data, you start with the really messy data, since it's pretty easy to, let's say, miss a dot, miss a point here, miss a point there, and just completely ruin the relationship and the relationship between the edges. For example, if this type of data, we start from this really messy type of data, and we can see that for this type of data, there are loops. Loops, I mean, may be fine from, let's say, plotting perspective, may be difficult, let's say, when you want to run algorithms or estimate graph measures. There are overlapping intersections, there are repeating nodes, and there are roundabouts that may be unnecessary complicated if you want to, let's say, estimate some measures on the graph. So the first thing that I want to present is that we develop a node that can be used to simplify edges. Simplify edges means that we want to remove the loops, and for example, here you see that there are two edges that connect this node, and then there is a loop that connects this node. When we remove these edges, when we simplify this network and clean this network, we remove these edges. Then again, we can see that in this case, there is a sort of an overlapping between these two segments. And this is quite crucial since in my experience, when you work with OpenStreetMap data and you adopt, let's say, the algorithm that we use to transform line strings into SF networks, it's quite easy to miss some connection between the roads. This is quite easy since in OpenStreetMap, usually there are, let's say, some internal nodes that may be missed from the algorithm used by SF networks. This is a problem since, as I said, when you try to convert an object from a raw line string to an SF network object, you place a node at each boundary point. The problem is that if there is a connection between two streets, which is not the boundary point for both streets, then this connection is missed by the algorithm behind the SF network. So we implemented a morpher that can be used to simplify this structure, to fix this problem, and to add this missing node only if there is an overlapping between two segments that share a point. Then we implemented also another structure that can be used to remove the redundant edges. For example, here we can see that there is this node here. This node here is quite, it's useless from a routing perspective, since if you start from this node and you reach this node, then you can just go back or you can reach the other node. So it's useful from a routing perspective. And we implemented this algorithm to simplify this structure. The problem here is that when you start from let's say raw OpenStreetMap data, it's quite easy to miss this problem since, for example, if you check the plotting or if you check this plot, this one, I think that it's completely impossible to see if there is a missing edge, if there is a missing node, if there is a missing whatever all around the network. So the problem is that you can't manually fix this problem, and we have to manually manufacture, let's say, these preprocessing steps that are particular just for geospatial networks. Back to the slides. Oh, here. Also, there is, I think this is also another extension that we did over just union of SF and ID graph. So the problem is that there are some processing steps or some ideas that are just unique for geospatial network object, and these morpher or these functions are not present nor in SF nor in tidy graph. So we had to manually add this function to manipulate this network. Lastly, we also implemented a function that can be used to remove roundabouts or, let's say, to close intersection. The idea is that you want to merge all the nodes that are closer than a given threshold. For example, here we have this one, which probably represent a roundabout. If we want to just code a roundabout as a single point, we just have to merge these 4 dots as a single dot and create this structure. This structure is much simpler from let's say, from an algorithm and from a data structure perspective. And I think that this is really important, since when you work and you model and you code with this type of object, it's quite easy to, let's say, work with the object that are too big or too difficult, or they are cover non-interesting parts. And I think that this type of preprocessing steps are quite important if you want to properly model something that's happening on the network. For example, again, I want to stress that if you miss this type of preprocessing steps and you try to develop like a routing algorithm, it's easy that you miss some connections between the streets. And if you miss this connection, then you maybe miss some shortest path on the network. So it's quite crucial that if you work with this type of data, you apply this preprocessing function before working with the data. Also, there are some other preprocessing steps that I didn't mention here. So there is, let's say, this is not really a function, but it's just, let's say, an example that it's added in the vignette of the packet that show how to, let's say, round the coordinates of the points. As I said, the nodes are just placed at the unique boundary points among the segments, and there is a connection if and only if two segments share a boundary point. The problem is that clearly we are working, let's say, in a finite approximation world. I mean, the so-called FAQ in the R code. And so the problem is that if you try to test if two nodes are equal, it's quite easy that the code, the R says that two nodes are not equal just because that there is a finite approximation in their coordinates. So there is an example in the vignettes showing how to round the coordinates and to approximate these coordinates. So back to the demo now. No. Okay, so I mean, I don't want to add any more details here. I just want to say that if you want, you can just chain all the preprocessing steps one after the other. The preprocessing steps are coding in a set of morphers, and I will add more details in a few moments. These morphers are used to just convert between one representation and another representation of the network. So we start from, let's say, the untitled network, then we apply all the preprocessing steps, and we arrive to a simpler representation, and applying all these preprocessing steps. Takes just a few seconds. Okay, I'm running a little late, so I will skip the printing and the plot. I just want to say that here the convert function is a function which is defined in tidy graph. This convert function is used again to apply a morpher. A morpher is a function again which is used to convert a network between one state and another state. So for example, here we convert this function from the raw state to a state which is defined by the function to spatial subdivision. The idea is just to convert this network to this other type of network, where this other type of network is defined by the application of the function to spatial subdivision to this type of object. So, as again, let's say the main strength of the tidy graph approach is that you can modify the edges and the nodes using the super common dplyr and tidy verbs. For example, in this case, we start from the result of the preprocessing operation, and we add a column named degree. This column named degree measures the so-called centrality degree of the nodes. We add the column using the dplyr function mutate. And the centrality degree is a concept which is typical of the nodes. And if we won't be sure that we are working with the node table, so we use this operator to set the node table as the active table. We can also apply something similar to the edges. This type of code is used to create a new column in the edges table. This new column is named weight, and this new column measures the length of each edge. The length of each of the edges is a concept which is not, let's say, I think, super defined in the tidy graph package, and it is another extension that we added with the submitters. If we run this type of code, then we can also compute a weighted graph measure. For example, this type of code is computes the weighted edge between a centrality, where the weights are defined in the weight column. The weight column measures the length of the edges. Okay, so let's see the printing of the object. First, we can notice that the object has less nodes and less edges than the original object, since several nodes and several edges were discarded during the preprocessing steps. We have the same coordinate reference system, and we have that the active table is the edges table, and we have that for this table we have the same column as before, but two new columns which are named weight and betweenness. The first column again measures the length of the edges, and the second column measures the betweenness, the centrality betweenness of this node. And these measures were added using the mutate verbs displayed above. With this code, we can also represent the plotting of the SF network object. As I said, the SF network, I mean, at the moment, we did not code anything, let's say, more advanced for the plotting operation. So if you want to plot something more advanced than the first example, you need to manually extract the nodes, extract the edges, and manipulate these structures. This is quite important since, as I said, the SF network object is more or less a union of two SF tables, one of the nodes and one of the edges. And you can always extract the table of the nodes and the table of the edges. If you want to extract just the table of the nodes, you have to run st as SF, then you have to pass the SF network object, and then you have to specify that you want to extract the nodes. For example, this is the output of st or st as SF nodes. Here we have is a simple feature collection with features. The same code holds for the edges, and this is important since when you extract the SF structure for the nodes and the SF structure for the edges, you can just run the geom_sf function and create a ggplot object starting from the two parts of an SF network object. In this case, for example, this plot represented the same SF network object as before, but the edges are just represented as gray lines. The nodes are represented as dots, where the color of the dots represented the degree of the node. We can see that, I mean, clearly there is an higher degree close to this part, which should be the main city in the Isle of Wight. And we can apply something similar also when we are working with edges measures. For example, with this code, we are trying to represent the edge between a centrality measure. Again, the segments will be colored according to the estimate of the edge between a centrality measure. And it's represented here. So the idea is that we start from the data which is obtained from SFNet, from OpenStreetMap, that represent the location of the edges and the roads and the road network in a place. We convert these, let's say, raw data into an SF network object. After the conversion, you can apply everything which is defined in tidygraph, and you can manipulate and you can estimate new measures that might be relevant for the spatial structure that was downloaded from, for example, from OpenStreetMap. Here, I just want to again underline that when you work with this object, you must be sure that you are working with the right column, so with the right table, and you must be sure that the right table is marked as active. For example, the centrality edge betweenness measure does make sense only for the edge, so you cannot estimate these measures when the nodes are marked as active, and this returns as an error, and says that this color requires edges to be active. There are some small details that should be specified. I mean, I just add a few sentences now, but you can check the vignette as always. There are some dplyr and tidyr verbs that cannot be applied to SF network object. The problem is that you can only modify, you can only, let's say, add or remove column or filter rows, but you cannot change the structure of the network. So for example, you cannot add a summarize, you cannot apply a summarize verb to this type of object. And because, I mean, the same problem holds also for tidygraph objects. And if you want to extract the coordinates of the nodes or the coordinates of the edges, you can just run st coordinates. For example, these are the coordinates of the unique nodes that define the SF network objects. These are the unique nodes that define the edges. Then, I mean, as I said, the SF network, again, I mean, I'm sorry that I have to repeat it 2,000 times, but the SF networks package is the union of SF and tidygraph. I try to briefly present some of the function that we imported from tidygraph, but he also extended some of the function in SF. For example, if you start from an SF network object, you can try to change the coordinate reference system, which is used to represent this type of data. And this type of code is used to convert the data obtained from OpenStreetMap to another coordinate reference system. This coordinate reference system is proper for the England. It's like a projected coordinate reference system for England. And again, this is important for all packages that cannot handle projected coordinates. Then we extended, the function stFilter to apply binary spatial geometry predicates to SF network objects. For example, the idea is that maybe you start with this type of data, this one, and I mean you start from the whole island, and then you want to focus just on the center, on the capital. If you want to focus just on the area, you can apply a spatial filter. For example, in this case, I tried to select only the nodes that intersect a buffer. A buffer is defined starting from the centroid of the network and apply a 5 kilometers buffer. So first we estimate the centroid, we estimate the buffer, and then we filter only the nodes that lie in this buffer. So I think that is pretty clear from this plot. Okay, so the black part is the, let's say, the total SF network object with nodes and edges. The gray circle, the orange circle represent the polygon that is used to define the spatial filter, and the red and the red points and the red lines represent the nodes and the lines that lie inside the spatial object. I mean, I don't want to add more details now. The only thing that I want to add now is that when you work with stFilter, it must be important to work with the, I mean, it's different if you're working with the nodes or with the edges. The problem is that, I mean, at least also from a graph perspective, there must be nodes that are connected to no edge, but it's impossible to preserve an edge and remove the corresponding node. So, for example, in this case, you can imagine that, I mean, if I remove this node here, where there is the mouse, then I have also to remove the corresponding edge, since the edge is the union of the nodes. If I remove the node, I have to remove all the edges connected to that node. The problem is that when you apply stFilter and you want to filter according to the edges, then you will preserve all the nodes. For example, oops, sorry. For example, in this case, I take the SFN clean object. I apply a special filter, and then I try to plot the only, let's put a color. And I take the SF network object, I filter only the observation that lie inside the buffer, and then I plot. The problem is that when you filter this observation, you preserve all the nodes, even the nodes that do not lie inside the buffer. Since in this case, you have filter according to the edges. If you filter according to the edges, then you remove all the edges that are not inside the buffer. The problem is that in this case, you preserve all the nodes, since the node can exist only if there is no edge attached to the nodes. In this case, I just want to present a simple example showing a tip, I think, in my opinion, showing two examples. The first one is a set of code that can be used to create toy SF network object. So the problem is that usually when you want to test a new operation, you may download the data from OpenStreetMap, then you can create the SF network object, and then you can test your new algorithm or new function or whatever. This type of code, I think that is a super simple example that shows how to create an SF network object, which has a special meaning, which has a special component, and I think it's much simpler if you just want to create some toy example. In this case, okay, perfect. we are using the play geometry function. This play geometry function is defined in tidy graph. The idea is to create 200 nodes and saying that two nodes are connected if and only if they lie closer than 0, 1. The nodes are randomly placed in the unit square. And I think it's quite clear from the plot. I have to run it all together. So in this case, we have this super simple example. I mean, this is not a realistic geographical network, at least from a road network perspective. Still, if you want to, let's say, just test some code, test some plot, or test something, I think that is a useful approach to plot SF network, to create a toy SF network object. Then I want to present just, I think, is a small tip, saying that if you want to filter the nodes that lie inside the polygon, I think that usually it's it's faster to run the st contain predicate instead of the st intersect predicate. I mean, the difference is usually really, really small. For example, in this case, I create a node with like 1 million nodes. I mean, it's impossible to represent this node, but okay. And I try to filter only the node that lie inside this polygon. This is a polygon that goes from 0404 to 0606. And the point that I want to stress is that usually it's faster to create an index for the points that are contained into the polygon and then just filter according to the indices, then just apply ST filter. So, then, I mean, this code usually, I mean, it's much more complex. I mean, doesn't look as good as the other line of code. And as you can see from the system.time, the difference is not enormous, but still, I mean, it may be nice if you're usually working with large SF network objects. I hope that it's working. Let's run it run. As you see, I mean, the difference is not incredible, but still usually is much better to just create an index for the points that you want to retain and then just filter those index, then run ST intersects. I think that the point is that usually it's easier to just say that if a polygon covers a point, then if a point intersects a polygon, but I mean, I'm not super sure, I just want to share this fact. And to conclude this part, I want to share a plot that represents this example. Oops, this one. And so again, we can see that there are many points, and we are just filtering the nodes that lie inside this part. Also here, I just want to stress that the implementation behind SF network is not optimized for speed, is not optimized for RAM usage, but still it's quite good, since if you imagine we are working with 1 million points, and with these 1 million points, we are running a filter, and that takes just 8 seconds. I mean, I think that it's pretty nice. I mean, we didn't code anything like that. I mean, we are creating just a wrapper, but I think that we created an efficient wrapper. And if there is any question, I can answer the question now since there are just 8 minutes left. Otherwise, I can just present the last section.
Okay, yeah, thanks a lot so far. So we have a few questions. I don't know, shall I read them first and then see if there's still time to continue?
Okay. Let's see the last part. So the super last part is the estimation of the shortest path. Do you see my screen?
Yes.
Okay. For the shortest path, I mean, the shortest path are, I think, probably one of the main reasons why we developed the SF networks, since the problem is that when you want to estimate distance on a graph object, it's quite difficult if you just want to use SF or if you just want to use tidy graph. The idea is that you want to measure or to try or to optimize a path between 2 points, constraining the paths just to the lines that are placed in between 2 points. For this reason, we implemented several wrappers that can be used to estimate shortest path. For example, for this example, I will try to estimate the shortest path that lie between the two random points in the Isle of Wight. The idea is that there is a function which is named ST network paths. The input of ST network paths is the SF network object, the starting point and the end point. The SF network object, then there is an algorithm which tries to estimate the shortest path. The start and the end points usually do not lie exactly in the nodes of the network. Usually there is the usual problem of the rounding of the coordinates. If this point do not lie exactly in one of the nodes of the network, then they are just projected to the nearest feature. So we just match this random point to the nearest point of the net, to the nearest edge of the network. The same holds for the endpoint. The output of this function is a table with two columns, one named node paths and one named edge paths. Both columns are list columns that summarize the indexes of the nodes and of the edges that compose the shortest path. This is quite useful since if you want to display or subset the shortest path, you can just use these indexes and select the shortest path. For example, in this case, I take the output of the object, I take the SF network object, I extract the geometry representing the edges, and then I again subset according to the indexes of the path composing the path of the edges.
Maybe Andrea, you should leave some time for questions because your time is running out. It's only 5 minutes left.
Just one last plot.
Okay, please.
And for the last plot, I just want to show the shortest path between the 2 points. Again, we have the green one is the starting point, the orange one is the last point, and the blue path is the shortest path between the 2 points. This path is weighted according to the length of the segments. There are many more details, but I cannot, please check the slides or write me an email.
Thank you. Is this functionality, the shortest path, this already existed in, was it in what's the name of the package?
No, the functionality already exists in a graph, and there is a wrapper entitled graph around the graph. The problem is that it's quite difficult to estimate the shortest path between 2 spatial points and in a SF network object, since you have to match these spatial points with the nodes, and then you have to extract this path. So we did not code the algorithm for the shortest path, since the algorithm for the shortest path is already coded in a graph. We coded a wrapper behind this function, and we coded the approach that can be used to use this shortest path with SF objects.
Okay, let's do the questions. Thank you.
Thanks a lot, Andrea, for the great introduction into SF networks. We have a few questions on Mattermost, and 2 of them are related to speed. So there's a question, I just wonder, how does the routing speed of SF network paths, which as far as I understand uses iGraph, which in turn is written in C under the hood, compares in speed with OSRM router that is written in C? I wish it was comparable in speed, then we would be able to do routing without any external software. And the second question related to that is, what about the CPP routing package, how that compares in terms of speed?
Now, for the moment, we didn't run, let's say, any speed comparison test, since the point is that we try to wrap the package which implements several aspects to work with geospatial network without focusing on routing. So probably, the packages and the functions that are specialized on routing of networks are faster than our approach, and probably because we decided to implement a package that covers more aspects of working with geospatial networks. We didn't run any proper test at the moment, but we may run some tests in the next days or next weeks. In our case, our code is just a wrapper around the iGraph code, so I think that it's pretty fast. The only downside at the moment is that the iGraph code does not implement the so-called many-to-many routing. So if you want to estimate the shortest path between endpoints and endpoints, that's not implemented. You can estimate the shortest path between 1 point and 1 point, or the shortest path between 1 point and endpoints. You cannot, let's say, estimate a matrix of shortest path, just vector of shortest path, let's say. And I think that's the main drawbacks that I know with this approach. There are so many benefits of just wrapping a graph function, since, I mean, it's an incredible package. And that's all I think. I mean, I don't have a precise answer on the speed comparison, since we did not run any tests for the moment. We may run some tests in the next weeks and then publish the result on the website.
All right, then we have two questions about pre-processing and cleaning. For lines that intersect but do not have nodes, there might have been over or under passes and thus shouldn't have a node. Are there ways to identify these non-intersections during the cleaning? And the second question about the pre-processing is, what about one-way roads or one-way vectors?
Okay, so for the one-way roads, I mean, in the example that I presented here, I try to ignore that there are one-way roads and assume that both roads are two-way. The problem is that in a graph it's not possible to mix one-way and two-way roads, but there is an example in the package, in the website of the package, that show how to mix the two approaches, I mean, the two cases. And for the other stuff, I mean, if you want to check if two segments are intersecting, but they are not, I mean, they are just like an overpass, I think that you can use just an ST intersect after the preprocessing steps. The idea is that you pre-process all the intersections that are truly intersection, since they share a node. After you pass all the preprocessing steps, then you can check with ST intersects or ST overlaps, or I mean, any function that says that there is a common space. Then if there is a common space and that space is not a node, then I think you can say that that point is an overpass or a bridge or something that says that two streets are overlapping but are on different levels.
All right, okay. I see we run out of time. There's one open question left, but maybe you can answer it in the MetaMost channel.
Well, you can ask. You can, if it's the last question, you can do it.
All right. How to calculate the length of a shortest path? Is it straightforward to determine what the shortest path is? Yeah, that's a question.
Yes, because there is a wrapper in, there is a morpher in the package, which is used to subset only the edges that belong to the shortest path. If you just want, to length of the shortest path, then you can just subset all the edges that belong to the shortest path and then sum their length. Then I think that there are some functions that are coded in a graph to estimate this type of measure. For example, if you want to, there is a function which is called, I think, distances. And then if you extract the indexes of the edges in the shortest path, then you have to extract the corresponding elements in the matrix and sum the elements in the matrix. I'm not sure if there is like a built-in function to just extract the length of the shortest path. I have to check. I don't think so, but I have to check. But in any case, it's pretty easy if you want to just manually code a function to extract this information.
Okay, we have to stop now. Thank you so much, Andrea. Yeah, fantastic that you're making this package, and looks like
thank you.
Looks like so many applications. So Hannah, you want to close the session, please?
Yeah, I can close the session by thanking Andrea again for the presentation and also the other speakers of today. And we will meet again tomorrow to continue with the third part of the summer school.
Yes, so we see you all tomorrow, and tomorrow again 5 interesting talks, including one open discussion panel on R spatial and future of R spatial. So we see you tomorrow. Thank you. Bye-bye.